Hey everyone, my name is Denise. I'm an engineer at Meta working on our video quality of experience team in video infrastructure. I'm here today to hopefully give a quality talk on video quality metrics and how we use these metrics to drive better quality of experience outcomes on our services. Most engineers recognize the value of metrics to understand the health of their service and hopefully detect anomalies. But what I'll talk about today is how we also leverage these metrics to make better real-time production experience that should hopefully lead to a better quality of experience when watching videos on Facebook and Instagram. So as an engineer on the video quality of experience team, we're responsible for making sure that your videos don't look like the one on the left, overly pixelated with scaling artifacts. We also want to make sure that you don't have to sit through overly long spinners waiting for your video to start, or see spinners when you're just getting to the best part in the video. There are also times that we've had to step up and manage our data usage. As an example, in the early days of the COVID lockdown, as you might remember, everyone had to switch to online, to work, for school, for their entertainment needs, and this put a lot of load on networks around the world. So we had to do our part to reduce at least the traffic coming from video streaming and achieve the right balance for users. So what do these problems of video quality of experience and managing traffic have in common? It's about balance. So again, we want to make sure that we balance having good quality without stalling and while using a reasonable amount of data. And sometimes this involves trade-offs. So for example, you can play the highest quality possible, but you might have a higher risk of stalls, or you might use more data, or you can minimize your chances of stalling and you might get potato quality or something that's overly pixelated. So to make these trade-offs, we really need to have a good way to measure all of the things involved. So the stalls, the quality, the data usage, and also the video quality so that we can make the best optimized decision. Today, I'll take you through our video quality metrics and talk about a couple of applications, both in how we enforce quality limits on cellular networks and how we use these quality scores in our adaptive streaming algorithms, and touch upon some future work in this area. So let's get started with our video quality metrics. So to start with, we need a way to predict how a human would perceive a video on our system. Ultimately, get everyone in a lab, rate everything on a scale of 1 to 5. Doesn't really work when you are operating with billions of videos. So we need a metric that will predict this quality score. So traditionally what we've had is an SSIM-based metric to measure in a full reference way the difference between the quality of the video that gets uploaded to our system and then what the user actually sees. So let's start, a user has a video on their phone, they might capture it inside the app or just capture it normally on their device, and they need to upload it to our service. Many times this involves transcoding the video to a lower file size on the device even before it's uploaded. From there, we ingest the video into our system and we need to encode a full ABR ladder, potentially many in different codecs. And again, using different quality presets, different resolutions, we end up with multiple encodings to choose from. Then on the client has to decide based on network conditions, device settings, say the amount of data already buffered, what's the best quality to play at any given point in time. And finally, this video might be viewed under different circumstances. So for example, auto playing in feed, full screen and horizontal landscape consumption, or maybe even on a large screen like a laptop or a connected TV. And we know that if we look at the difference between what was ingested and what we actually played in a given viewport, this is how we compute what our quality score is. So again, to start with, we had an SSIM-based FBMOS score that served us pretty well. However, we started to see some limitations of the system. Again, in general, if the score was going up, we knew that quality was getting better. But we found that there were specific examples of video that we were overly penalizing. So this video of this tree, for example, left is the original, right is what we encoded as one of our lower bitrate encodings. The one on the right is degraded. It doesn't have quite as much detail. but it has an FEMA score of 8. And to be honest, I don't think it's quite as garbage as the score makes it seem. Like, it's still pretty watchable. But we've seen that SSIM will overly fixate on a lot of details that might not be quite as salient to the average human who's actually watching this video. And we wanted a way to deal with this. So next we looked at having a VMAF-based solution. So VMAF is, again, another perceptual visual quality metric that's well used in industry. And it's great. It has much better accuracy than our SSIM-based solution. But the trade-off is it also consumes a lot more compute. And again, at our scale, with the number of different videos we have uploaded every day, we just can't afford to use all of this compute on every single video to achieve a more accurate metric. So we had some decisions to make. We wanted to use this, but we had to make it more scalable. So the first thing we did, not all videos are VMAF eligible. So for example, a creator uploads a video that we predict will get hundreds of millions of views. Yes, we can spend a little bit more compute to get a more accurate score. I upload a video that maybe might only be seen by my closest friends and family, probably not VMAF worthy. So we make some decisions based off of that. I mean, again, we still have SSIM. We don't have nothing, but we understand its accuracy will be more limited. Additionally, we see how can we actually make VMAF faster. So we leverage techniques such as better frame subsampling to speed up the compute of VMAF. We're continuing to evolve our outlook on this. So for example, we've done some work with UT Austin on Funky. And this, again, will have multiple operating presets, really evaluating the trade-offs between metrics accuracy and compute costs. So we have some papers published on this. So at this point, we have a quality score on a scale of 0 to 100, representing how good we think the content looks. But rather than just this continuous scale, we also really want to quantize this into discrete buckets. We don't think that human perception will necessarily perceive the difference the same at all points in the scale. So this is based on work that we've done with the University of Nantes to really understand the acceptance annoyance. So we think that there's, again, a certain quality level that if you go below it, the video is just not acceptable. Like, you've all seen kind of like pixelated garbage videos and you don't want to watch them. They don't look good. We don't want to serve them. We want to avoid being in that bucket. Then you might have, it's kind of annoying. You'll watch it, like if you care enough about the story, if you care enough about the content, but you're not going to love it. It's going to be notable. And again, like, we'd prefer not to serve that. Sometimes the network is just very limited and you have no choice, but we really would prefer not to be in that bucket either. And finally, you have not annoying. So again, it's not to say that there's no difference, no notable difference once you're in the not annoying bucket. But you would see that it satisfies the goal. It satisfies the goal of what you're trying to do with that video. And this is really the point that we want to be operating in. We've also done work that shows that, again, that perception of which bucket you're in depends on the context. So one case that we've looked at, again, with the University of Nantes, is how does the user's perception of quality, how is it influenced by device constraints? For example, if we prime you to think that you're almost out of battery, or if you think that you might be running low on your data plan. And what we saw is that users were actually a little bit more willing to accept lower quality when they had these device resource constraints. So let's recap where we are. So we have, again, a better compute scalable score on a scale of 0 to 100, ideally VMAF when possible. And we also have an understanding of where these inflection points are with our acceptance annoyance scale. At this point, I want to start talking about how we actually use these scores to make better decisions. One application is how we think about limiting quality on cellular networks. So we might want to do this because of data costs, or in cases like we talked about with COVID lockdowns. And we need a solution that scales across an array of diverse content, everything from reels to premium content to like live streaming of gaming, and ensure that we maintain a good minimum quality bar across our experience. So there are different ways you can do this. Traditionally, maybe it would be done by resolution, like we support HD quality or we support DVD quality everywhere. or bitrate. Like maybe we don't allow anything above 2 megabits per second or 1 megabit per second. But what we really wanted to see is like, how can we do this in a quality aware way? So just like I think it's pretty well accepted that constant quality encoding is better than constant bitrate encoding, we wanted to bring a similar concept to the way that we looked at cellular data limits. As an example, this is showing on the x-axis a quality score, a y-axis the distribution percentage of samples at each quality score for video encodings 400 kilobits per second using VP9 encoding. What this shows is that 400 kilobits per second of VP9 does not really tell you anything interesting about the quality in general. Again, you have some samples that have a quality score of 90, you have some that have a quality score of 40. So the bitrate itself is not a clear indicator of quality. This can also be seen on this graph. So here on the x-axis now, you have bitrate, on the y-axis you have quality. So let's say the blue line is one video, the orange line is another video. Each of these dots represents a given encoding with a given bitrate and a given quality score. And let's say, for example, you decided to draw a line at 500 kilobits per second. You can see that's fine for the orange video. Maybe it's very simple. Maybe it's using more advanced encoding like AV1, whereas, say, the blue video has a lot more complexity or maybe is using H.264. But that orange video, you would actually get a pretty acceptable quality in the 85 range. Whereas that blue video, 500 kilobits per second, you'd be stuck with something under 40. Okay, so hopefully I've convinced you quality is the way to go. So if we do quality limits, how do we actually define these MOS-based limits? What we want is a maximum quality score. So basically, do not exceed this limit. We want to make sure, though, that we still maintain a minimum quality bar, so at least one lane above a specific level. And just told you how bit rates were useless. They're not completely. They do make good guardrails. So we still have minimum and maximum quality bars that we enforce based on bit rate, just to kind of make sure that we're not doing anything too crazy. And finally, we also want some flexibility that we might be able to make different decisions depending on factors and contexts, such as, is this an intentional viewing situation? Or is this something maybe that's autoplaying that the user hasn't committed to yet and making different decisions based off of that? So let's go back to some graphs. So again, x-axis is bitrate, y-axis is quality. Each of these different colors, so the purple, teal, fuchsia, represents a different video, and each of these dots is a different encoding. So if we want to define these MOS-aware avoid-on-cell rules, first we have this horizontal line, which is the maximum MOS. This is our do not exceed, don't play qualities above this line. For simplicity, I removed the minimum MOS. But we also have these vertical lines representing our minimum and maximum bit rates that we want to use. The minimum bit rate might be, again, it's not really visible in this example. Let's say the video is like super simple, and even at like 300 kilobits per second, the quality is amazing. You know what? It's below the minimum. It's fine. Allow it. On the other hand, the maximum, again, this especially helps when maybe our accuracy is a little bit lower for some of our SSIM-based rules. But it might say like, okay, we'll give you up into, in this example, say like 1.6 Mbps. If that's not enough to achieve your quality goals, we're stopping there. So we're still going to have some bitrate cutoff to make sure that, again, the bitrate isn't too high. So what you see, again, using these thresholds, again, for these three different videos that have different characteristics, again, maybe the complexity is different, maybe the encoding is different, we're still able to kind of enforce a uniform user experience. Again, they have relatively similar quality scores, even if there's a little bit of variance in the bitrate. And again, this avoid on cells doesn't tell you what you have to play. It's just a ceiling. So if your network conditions aren't great, you still might have something lower, but this is the ceiling that you would play. So let's recap. What are the benefits of this MOS-based avoid on cell system? So we maintain a consistent user experience. We also reduce the incidences of just playing really terrible quality because we don't understand that, hey, this is a video where we might just need a little bit more bits to achieve good quality. We can deliver at or better equivalent data savings as something based on bitrate or resolution. And it really allows us to optimize our usage on metered connections. Next, I'm going to pivot and talk about how we use quality scores in our adaptive streaming ABR algorithms. So a long time ago, there are times where we wanted to, for example, introduce lower bitrate lanes to really accommodate users who might be on more limited networks. And what we would see is we would introduce these low bitrate lanes, and all of a sudden we would see users using it too much, having negative experiences, and ultimately using our service less. And this isn't something that we want. Again, we really want to balance, again, the risk of stalls with the benefit of higher quality. So what we decided to do is really make the video quality of each selection an option in our algorithm. So again, to recap how the ABR algorithm works, you as input are given a dash manifest with a bunch of different qualities to choose from, each with different quality scores, different bit rates, different URLs to use. You also are looking at how much data do you have buffered, and what is your network conditions, what's your bandwidth estimate, and given all of those factors, the player has to decide which one do I use next. What we realized is that the trade-off between the quality and the risk of stalls is not uniform across all of these lanes. So I'm going to switch back to some graphs to walk through some examples here. Let's go back to our orange, I call it orange before, and our blue videos. So again, what we see is that to the left of this graph, every bit that you allow basically gives you a much higher gain in terms of quality score. So if we were looking at this, you see on this blue video, we actually have some lanes that would have a quality score of 15 or 20. That's not great. We would prefer not to serve those unless you really, really need to, because your internet connection is just not able to support anything higher. So at this point, we'd be willing to take a little bit more risk of stalling, be willing to wait a little bit more time for the video to start to make sure that you're at an acceptable quality, maybe even a little annoying, but at least not in that unacceptable bucket. So we're willing to take a little bit more risk on stalls. On the other hand, let's look to the right of this graph. You've noticed the slope of these curves flattens out quite a bit. Let's say for this video, again, the dots that are second to the right, quality scores are pretty acceptable. Hopefully, we don't think they're very annoying. It still can be improved. Like the one all the way to the right is probably going to look better. And it's what we would prefer to serve if we could support it. But it's not worth risking a stall to achieve it. Again, you have gigabit internet, 100 megabit per second bandwidth estimate, like go for it. You're probably fine. But if we think that there's a chance of stalling, we're better off like not taking that risk and play the quality lane that we know is good enough. So this is how we factor the quality scores into our decision-making in ABR in a way that we think really leads to a better trade-off between visual quality and stalls. With my last few minutes, I just want to kind of touch upon some additional future work in this area. So the first thing you might remember, if you remember my complicated diagram from many slides back, we look at the quality score as a difference between what we ingested and what we played. But we don't necessarily only get to ingest like pristine studio quality content. People like to upload videos that like maybe has been forwarded around the internet a number of times, like sent to multiple WhatsApp groups and downloaded, gone through multiple generations of like transcoding loss, and then finally uploaded to our system. So we really also need to augment this with no reference metrics to really get a better understanding of what the user is seeing. No reference metrics are harder. It's an area of academic research. It's something that we're participating in. So we know that there's a challenge, but we would really like to incorporate more no reference metrics into our algorithms. Another avenue that we're really pushing quality for is HDR. We know that it makes our content a lot more vibrant, and we're really proud to be able to support that across Facebook and Instagram. It also comes with its own challenges of how to measure quality and how we take that additional vibrancy into account. So again, this is an area of active research and something that we're continuing to iterate on. And then finally, I mentioned that we're really trying to balance the compute costs of visual quality metrics with its accuracy. So Funky Plus, Again, these are all additional projects that we're continuing to invest in to really find the right balance that works for a service such as ours that hosts a lot of user-generated content. So thank you for all of your time today. I will stick around for questions. Feel free to reach out, and hopefully you learned a little bit and let me know what you think.